This is the video for Lab 3, Calculations and Report. It's on the use of volumetric ware and the determination of density. There was an earlier video on Lab 3, and you can consult that, where I actually demonstrate the use of those pieces of equipment. Here we'll look just at the calculations and report. So let's begin with the pre-lab review page. And question number 1 is always the same in each of the labs. Are there any safety alerts? And from this point on, the answer will probably always be yes. And in this case, there's one in Part B. So have a look at Part B. Question number 2 is also always the same from one experiment to the next. Are there any specific disposal directions? And what you'll do is you look through the experiment is look for the garbage can symbol, and that will be your clue. Question number 3, what is a meniscus? Meniscus is introduced in Part A, Figure 3.2. So have a look there. And question 4, where is a liquid volume reading taken in relation to a meniscus? Well, a meniscus is a curve like that, and Figure 3.3 will give you some guidance. These next two questions are rather detailed, and I don't believe they'll cause you any significant problems. Let's look at the next page. Question 7 in the pre-lab review says, what type of weighing technique, direct weighing or weighing by difference, is used to determine the mass of water samples? You can tell by looking at the data pages. If there's only one blank, that's your clue that it's a direct weighing. If there's 2 blanks, then you're weighing by difference. Question 8 and 9, no problem there really. Question 10 gives you a volume of exactly 12 milliliters, and it says, and it asks what you should record if you use a graduated cylinder. Well, remember that graduated cylinders are accurate to the 10th. Burettes are accurate to the 100th. So let those facts guide you. Question 11 won't be any challenge for you. Let's look at the first table. This is in the data and report pages now. Part A deals with the graduated cylinder, and it asks students in Part A to measure out a volume of water equal to 10 milliliters. And the graduated cylinder, the manufacturer tells us, is accurate to the 10th. So you'd want to be sure and respond by writing down 10.0. When you record masses, you'll use the photos that are supplied with the experiment, and the photos let you read the weights, the masses, to the 1,000th. So be sure and record to the accuracy that you can using those photos. As an example, the mass of the empty beaker I've written down is 31.420. And keep in mind that with all my numbers here, they're hypothetical. They aren't the numbers that you'll gather, with a few exceptions. That 10.0 is the number that you'll use, but the other numbers I've just made up. In the report for Part A, you'll transfer some of this data. The water volume for samples 1 and 2 is 10.0 milliliters. The water volume on the mass basis, well, you use this data over on the left-hand side to subtract, following the rules for significant figures. Since you have 3 decimal places, the water volume on a mass basis will be recorded to the 1,000th also. Then to get the volume difference, you'll subtract the lower number from the upper number. Following again the rules for significant figures, the upper number is to the 10th, so the volume difference has to be expressed to the 10th. The average volume differences, or difference, you'll add those two volume differences together and then divide by 2. So you'll find that it's also to the 10th. The average percent difference, when you calculate percent, would be equal to the 0.1 divided by 10 times 100. Or, in other words, we just be moving the decimal one place. So the 0.1 becomes 1. One significant figure in this case. Let's look at part B. Here we're using the pipette. The pipette has only one marking, not like the graduated cylinder, which has a series of markings. And so we rely on the manufacturer to tell us the accuracy of the pipette. And the manufacturer says that we can record to the 100th. So you'll record 10.00 milliliters for the pipette volume. The masses, again, are to the 1,000th. You can read the photos to that accuracy. And notice that the difference between these numbers, sample 1 would be the difference between 32 and 42, or about 10. And the difference between the first sample and the second sample is also about 10. Over on the right-hand side in the report, we'll repeat the reading basis for the volumes, 10.00 milliliters in each case. The water volume on the mass basis I got by subtracting the numbers on the left-hand side. And now to get the volume difference between these two bases, we subtract. Because the upper number is to the 100th, my answer has to be to the 100th. And in the calculations and report page, it tells you that if the upper number is larger than the lower number, then the volume difference will be a negative. So be sure and put that negative sign in there if your data is similar to mine. So, for example, I find the volume difference is a minus 0.06 and a minus 0.08 for sample 2. Adding these two numbers together, dividing by 2, gives us the average volume difference of 0.070, keeping those two significant figures that we have. Notice that when you add 0.06 and 0.08, you get 0.14. We now have two significant figures. So when I divide by 2, that two significant figures carries over to the 0.070. And again, I've retained the minus sign. The average percent difference, we move the decimal one place, as we did in Part A, and it's minus 0.70. Let's look at Part C. Here we're using the burette, and the burette can deliver variable volumes. The experiment asks you to record an initial burette reading. The burette, the manufacturer tells us, can be read to the 100th. Actually, that would be the same result that we get by applying the rule one more place than the number of markings. The burette has markings to the 10th, so we can estimate to the 100th. So here's the initial burette reading. Sample 1 is delivered to a beaker, and here's the final burette reading for sample 1. Then that final burette reading for sample 1 is used as the initial burette reading for sample 2. The difference between these two values is about 10 milliliters that you're after. The difference between these two values is about 10 milliliters for sample 2. And of course, what we're using here is the principle that 1 milliliter of water weighs 1 gram. And so we can test the accuracy of our volumetric ware by weighing the water sample. And again, as you look at the photos for the weights, you can interpret those photos to the thousandth. So be sure that in these 3 blanks you record to the thousandth. For the report on Part C, I've subtracted the initial burette reading from the final to get sample 1. The final burette reading for sample 1, I've subtracted that from sample 2 to get the volume for sample 2. The mass basis, you'd get those by using the weights that you have in table 3.5. And then I've pulled up some hypothetical numbers here for the volume difference. That is, subtracting the mass basis from the reading basis. And because these numbers are to the hundredth, my volume differences are to the hundredth also. And I've just pulled up 2 arbitrary values, 0.06 and a minus 0.01. That minus I would get if this upper number were greater than the second number, the number below it. And now the percent differences, we'd move the decimal 1 place to the left, so we'd get 0.6 and 0.1, retaining the negative sign. To get the average percent difference, I'd add these 2 numbers together. A minus 0.1 would make this 0.5. And then if I divided 0.5 by 2, I'd get 0.25. And following the rules for significant figures, we just want 1 significant figure. So I'd round the 0.25 up and get 0.3. Let's look at Part D. Part D, we're calculating the volume of a drop. And we're using 25 drops and 50 drops, initially placing those drops into a graduated cylinder and measuring the volumes. And again, my numbers, 25 and 50 are accurate, but these numbers over here will be different than yours. The graduated cylinder is read to the 10th. So I've recorded those numbers. Over here on the right-hand side, rather than dropping the drops vertically, we're dropping them horizontally. Numbers are a little bit different, but again, we'd record them to the 10th. And then using the burette to deliver drops rather than an eyedropper. Here's the initial burette reading. It's recorded to the hundredth. We're measuring out 25, 50, 75, and 100 drops. The initial the first burette reading for 25 drops is 1.08. That's my hypothetical number, and we'd have similar numbers down the line, increasing numbers. Now we're calculating the volume of a drop. And this is for the eyedropper part. We had 25 drops. You recorded the volume. 25 is an infinite number of significant figures, but you'll remember that when you recorded that volume, it was to the 10th, and that had 2 significant figures. So a grader will look for 2 significant figures here. Then in the report for the burette part, we've got 25, 50, 75, 100 drops. Here's a typical total volume for 25 drops, 0.93. I divide 0.93 by 25 to get this number. 2 significant figures, so I've got 2 significant figures in my answer. And then follow the rules for significant figures as you do these other calculations. And then there's a blank for the graphically determined volume of a single drop. It's important that you look for 2 significant figures here. If you have a whole bunch of significant figures, we know, the grader knows, that you really didn't use the graph. You used a mathematical determination to calculate this number. And we want you to use the graph. And the graph can only be interpreted to 2 significant figures. So make sure this number just has 2. Here's a typical graph down here. Yours might look a little different. Total number of drops is on this side. Over here on the vertical axis, the volume in milliliters. And if you need to review graphical calculations, go to Appendix A, or you can go back to Experiment 2. That's where we introduced graphing and the construction of a graph. So if you have some problems there, why consult those 2 resources. Part E, the density of an unknown liquid. When you have an unknown, the experiment will always ask for an unknown number. And remember that you get that when you enter ChemWeb. It'll say that your student laboratory ID is such and such, and it'll give you a 4-digit number. That number goes right here. We have 6 versions of the lab experiments, and so your number may be different than a friend's, so make sure that you use your own data when you're doing the experiments. Pipette volume to the 100th. Here you'll record mass volumes to the 1,000th. Then when you do the report part of this page, you'll repeat the pipette volumes as 10.00. I've put in a couple arbitrary numbers here for sample mass. Density, remember, is mass divided by volume, and that's how we've come up with this. In other words, the sample mass divided by 10.00 gives us this number. And we've got 4 significant figures, 4 significant figures. So my answer for the sample density has 4 significant figures. But now a tricky little thing happens. When I get the average sample density, I add the sample 1 value and the sample 2 value to get 1.9805. That's 5 significant figures. So my answer is going to have 5 significant figures. Let's look at part F. Density of a solid. You're measuring the density of a stopper. Masses again to the 1,000th. Cylinder readings to the 10th because you're using a graduated cylinder. Stopper mass, look for 3 decimal places over here. The stopper volume to the 10th. Stopper density will also be to the 10th. And again, my numbers are hypothetical. Let's look at a summary chart now for everything that we've done. The graduated cylinder, average volume difference 0.1, percent difference 1, pipette 0.070, and a minus 0.70, and 0.3 for burette. I hope those numbers help you a little bit. Let's look at the questions at the end of the experiment, and some of these are pretty hard and will take you a little time. Which of the following pieces of equipment is designed to deliver one specific volume? Look for the one that has only 1 mark. One of these 3 only has 1 mark. Number 2, suppose The calibration marks were 0.1. Which of these numbers would be the accurate volume? Well, remember the general rule. We can estimate one more place than the number of divisions. If we've got divisions to the 10th, we can estimate to the 100th. Number three starts a series of hard questions. And here's a little tip. Which of these errors in A, B, and C would result in more water? Tip for number 4, which error in A, B, C, or D would result in less water? Tip for number 5, ask yourself which error would give a greater volume? Number 6, which error would produce a greater mass for the liquid? And finally, number 7, water has a density of 1.00 grams per milliliter. Lighter things float, more dense things sink. Hey, I hope you have fun with the experiment.